Okay, so today we will finish the chapter 10 about this ANOVA. So have you watched the online video? Yeah, I found that it's really difficult to just give a lecture without having any audience. So I recorded my lecture, yeah, in a car. Yeah, so I mean, yeah, it was quiet, so it was nice, but yeah, I felt a little awkward. So, but anyways, I hope you had a main idea about some hypothesis testing that we are trying to solve in this ANOVA. And if you understood the previous setting where we have just one aspect that might influence the mean of different groups. Okay, so again, our main setting here is, let's see. So we want to test the hypothesis of. It is a little hard to find the. Okay. Let me try to find. Okay, so so we want to test these two hypotheses where the mean of different groups are all the same, or at least one of them is different from the other means. Okay, so that was the main task that we want to perform our hypothesis on. Okay, so we will still focus on this exact same task, but in a slightly more complicated settings. So the first setting that we will learn today is okay, so yeah, this one is about about some comparisons between the mean values. So suppose we in our hypothesis testing of H null hypothesis and H alternative hypothesis, and so again this one was all means are the same, right? But in the case of the alternative hypothesis, at least one of them is different from the other, right? But we didn't, so in this hypothesis testing, we didn't say anything about the potential differences or how much different these different means are, right? So we didn't quantify any kind of amount in terms of these differences between means. So we want to do this kind of task in this slide. Okay, so that is called this t-test. Yeah, I actually have not much of a kind of deep understanding about this, but I'll just follow this book and try to give some brief explanation about it. Okay, so let me just start with the example here. So here we have three different schools, and then they have some observations within each sample. So we have three samples, and each sample will have 4 different observations. So M is 3 and N is 4 in this case. And in this case, suppose we perform this hypothesis testing. Yeah, and then we after hypothesis testing, we concluded that we have to reject the null hypothesis, which means at least one of them is different from the others. Okay, so that is a current state, but what we want to do is to obtain this interval estimate between any pair of these two means of these groups. So we have 3 groups, and then we have 3 different pairs between the first and second and the first and third, and then the third, second and third groups. And then we want to obtain this kind of interval estimates in terms of this differences between these each pair of these two means of the two groups. Yep, so that is what we want to do in this case. Okay, so in order to obtain this interval estimate, we utilize this kind of confidence interval. So if you recall or remember what we did in this confidence interval or interval estimate, so we first think of this difference between the two parameters, and then we have these estimates of each of these parameters. So for mu I, its approximate estimate is represented as xi dot, which is like in this case. So this one is being I equal to 1, 2, and 3. So x1 dot means the average value of these 4. Okay, and then that way we obtained it. We compute this estimate of the true parameter of mu I and mu j, and then in terms of their difference, we compute basically the differences by using our estimate of these two true parameters, and then we have some uncertainties or some ranges represented by this w, which is representing some width of our confidence interval. Okay, and then just like the other interval estimate setting, we usually start with this alpha value. So that was the confidence level, right, in this interval estimate. And so if alpha was 0.05, and then we want to cover 95% of this probability ranges, or 95% of the cases by using this interval estimate. And then this W is represented by this equation. And that equation is proportional to this kind of thing, SS of W divided by nm minus m. And then this one was what? So this one was the first estimator for our true parameter sigma squared, right? And then so let me ask one kind of reviewing question. So is it a valid estimator for, is it a valid only when H naught is true, or is it a valid estimator even if it is not true, or even if H naught is true? H naught is not true. So is it a valid estimator regardless of the null hypothesis, or is it only valid when the null hypothesis is true? Only the null cases? Okay, so let me just go back to the definition of SS of W. Let's see. So this was the SS of W, and then SS of W is taking the square of the differences between these two, and then this one is our observation, right? And then xi dot is an estimator for the mean of each different groups. So it means we are using different estimate values of different groups' mean value, right? So in that case, because we are using different estimator for means of different groups, and so it is valid both for the null hypothesis when the null hypothesis is true or not, right? And then the second one, which was this one, which is using the common or the single or the same global mean estimator. In that case, this one is only valid when the null hypothesis is true, right? because it is assuming that across different groups they have the same mean value, right? So that way we took the differences between these two, right? And that's how we perform this hypothesis testing for this ANOVA's main task. Okay, so so this one is again, yeah, the estimator for this guy, regardless of the null hypothesis being true or not. And so yeah, this W is increasing in proportional to this standard deviation, kind of estimate of the standard deviation. Okay, and so it means that if sigma was really large, and then we have to have really a large interval estimate, because this sigma, I mean large sigma value will bring us really a large amount of an uncertainty, right? So I mean intuitively, suppose this was mu1 minus mu2 was maybe 1, yeah, between 1 and 3, and then maybe minus 5 and 10. So definitely this guy has the wider interval, right? So which one is a better interval estimate? This narrower one or a wider one? Which one is better estimate? I mean, which one would you like better? A narrow one, right? Because it gives a much more informative estimate, right? Okay, so yeah, this guy is a bad guy, right? If it gets large, and then it will give us a larger uncertainty, right? And then yeah, some value that we have to look at from our table. Okay, so yeah, honestly, I don't know how exactly this C is defined, but it is given as a table, just like the other kind of typical tables for F distribution and maybe standard Gaussian random variable and T distribution and so on. So it is something that you have to look at from your table that is initially given, and that way, yeah, we can obtain this width value in this interval estimate. Okay, and then from this equation, what we can, the information that we can obtain in addition to the the conclusion of the hypothesis testing, that the null hypothesis of having equal mean scores for students from these 3 different schools was rejected. And then among these 3 different schools, what is the interval estimate between the differences, I mean in terms of the differences between every pair of the 2 schools. So in this case, we obtained this amount and this and this. Okay, so after obtaining this interval estimate by utilizing or plugging in this equation, and then our conclusion is that mu1 and mu2, the interval estimate of this is definitely containing a 0 value, right? So we cannot conclude that they are significantly different from each other. But in the case of mu1 and mu3 and mu2 and mu3, their interval estimates are actually from this value to this, and then it's certainly, yeah, away from 0. So we have 0 here. In this case, the interval estimate was somewhere around here. But in the second case and the third case, our interval estimate was somewhere around here, right? So it's certainly excluding the 0. So it means that mu1 and mu3 and mu2 and mu3 are significantly different from each other. So that's the additional information that we can obtain by utilizing this equation. Okay. Okay, so yeah, so these are the answer that I just explained. And then let's move on to a little bit more complicated case of having unequal sample sizes. But it's really simple. So here the setting is as follows. So in this case of school example, so we have three different groups or three different sample, but now we consider the situation where the number of observations are different among different samples. So in the case of school, we had 4 students, but in the case of school 2, we had maybe 10 different students and their score values. Okay, and then maybe it has 7 students and so on. Okay, so that is it. So that is the setting that we are considering. Okay, so before actually going into the details about how to perform this hypothesis testing, I mean the overall or high-level scenario is exactly the same. So we compute the estimate of sigma squared by using the first proposed technique or first proposed equation, and then also we have another way of computing it only when the null hypothesis is true. Okay, so we are doing the exact same thing. And then what would you do when computing SS of W, this guy? Okay, so we can do just exactly the same thing. So we compute the sample mean from the first group by only using 4 observations and 10, and that way we obtain the sample mean of the second group, and then the third by using the 7 samples, right? And then we just subtract that value, the corresponding sample mean value from each of these observations, and then take the square of it, and then sum them up, right? So that is it. Yeah, that's it. And then in order to obtain this sigma squared, the estimate of sigma squared, after obtaining SS of W, what should be our denominator? So how much should we divide it by? So 4, 10, and 7. Can you give a number that should be placed in the denominator? So you guys remember the definition. First of all, you guys remember the definition of SS of W, right? SS of W is simply, let's see, yeah, this guy. So for each individual observations, we subtract its corresponding sample mean from it, and then take the square of it, right? So that is simple, right? And then after obtaining it, we have to divide it by some value so that we obtain this estimate of sigma squared. So what should be the value of it? So among the 4, it will have when using the sample mean, we will have 1 less degree of freedom for the first group, and then second group and the third group. So the total degree of freedom will be something like this: 4 plus 10 and plus 7 minus 3, right? Okay, so this is how we compute the estimate of the sigma squared by using the first approach, right? And then what about the second approach? Second approach was something like this. So this guy this guy is represented by this sample mean, right? X1 dot, X2 dot, and X3 dot, right? But here, this guy is actually normalized in this manner: minus mu, right? Divided by what? Square root of sigma squared divided by what? 4, right? So that's how we standardize the sample mean of the first group, right? And then in this case, the same thing: x2 dot minus mu, and then sigma squared divided by 10, and this guy x3 dot minus mu divided by sigma squared over what? It was 7, yeah. Okay, and then if we add them together, I mean after taking the square of it, okay, and then it will follow the chi-square distribution with the degree of freedom of what? What is the degree of freedom in this case? What was the degree of freedom? 3, right? Because we simply added 3 standard Gaussian random variables, right? Okay, and then the next step was what? We replace this common mu by or with the global sample mean, right? The average of all these samples, right? Okay, so in that case, the degree of freedom will be 1 less than the original one. So the degree of freedom will be 2 in this case, right? So the second way will still have the degree of freedom of m minus 1, right? But yeah, it has, so it has this value moving to the numerator and this value moving to the numerator and so on, right? So in the previous case, these values were all the same value as n, right? So in this original case, the n was all like a 4, right? But in this case, suppose this value was n1, so this is just a notation, and this guy is called n2 because these numbers are different from each other. So n3, okay, and then these different values are put or multiplied in the numerator. And then still the degree of freedom is m minus 1. Yep, so that is it. So if you had this kind of intuition or high level understanding, let's go through this. Yeah, let's see. Okay, so SS of W is going through first this different groups. So I is the index for the different groups, and then J is the index of the observations within each group, and then it will going from 1 through Ni, which is N1, N2, and N3 was 4, 10, and 7 in this previous case, right? So this is just a mathematical kind of representation. Okay, and then in terms of its degree of freedom was what? So 4 plus 10 plus 7 minus 3, right? And then 4 plus 10 plus 7 is represented in this form, right? And then 3 is the m, right? Okay, so that way we obtain the first estimate of this sigma squared. And then the second scenario was this guy. So we going from 1 through m, right? And then after taking the square of it, it's sigma squared divided by ni, which was like 4, 10, 7, right? And then if it moves to the numerator, and then it will have this one. Okay, and then in this case, the degree of freedom will be, let's see, m minus 1, right? And then altogether, the test statistic for our hypothesis testing is represented in this form. SS of W, and then divided by its degree of freedom, and then SSB, and then divided by degree of freedom of m minus 1. Yeah. Any questions? And then we still use the F distribution, right? And then the parameter is, the first parameter is this, and then the second parameter of F distribution is this guy. And then this guy is represented as the large N or capital N. Any questions so far? Okay, and then now let's move to this two-way ANOVA. Two-way ANOVA. So in this case, previously what we learned was called a one-way ANOVA, and then now we consider two-way ANOVA. So in the case of two-way ANOVA, so we had like these kind of 3 different schools in this case. Let me just erase it. Okay, so we wanted to test if there is any kind of significantly like a meaningful effect between different schools. Okay, maybe the students going to different schools are actually having all the same quality, or the first school is actually the students in the first school is actually a better students than the other those attending other schools. Okay, so we wanted to test such kind of a hypothesis. But in the case of two-way, so in the case of one-way ANOVA that we previously dealt with was, so this guy is not related to this guy or this guy. So they are just different students attending different schools, right? But if you remember some kind of paired test, paired setting. So when testing whether the average height of a person between Korea and US. So we collected maybe 100 people from Korea and then another 100 people from the US, and then each of these persons coming from Korea and the United States are actually a different observation. They are not related. But if we just consider maybe we collect 100 child when they were maybe 1 year old, and then we measure their height in Korea, and then they are actually moving to the US, and then we are measuring or obtaining the observations from the same people, and then that was kind of paired setting, right? So we kind of consider this kind of paired setting. So these are somehow all the same people or same person, and then the second one is the same person, and then the third one is also the same person. Okay. So in this case, we can think of like the effect of two aspects. So in the previous case, because these are just the different samples, and so we are interested only in like effects of different schools, which is corresponding to three different vertical kind of set or vertical kind of groups of these data items. But because we can now think of some meanings on each rows, and so we are interested in in testing whether different students have their own mean values different from different students. So the question is, those 4 students, are they actually having the same kind of a capability, or their averages are really different from each other? Okay, so that is the two-way ANOVA. So we consider the effect of the first aspect, and then also the second aspect, which is now has the meaning, which is now the meaning of different students. Okay, so that is the paired, this kind of two-way ANOVA setting. Okay, so such a setting, let's look at this brief example. So these are 5 different students took the 4 different exams. Okay, and then suppose, if we think of the mean value between different exams, suppose the third exam was really difficult compared to the other exams. And then the average value of the third exam, because their problems were really difficult than the others, so it will have significantly different mean value from the other exams. Okay, so that is the situation that we want to perform our hypothesis on. Okay, or the null hypothesis is all the 4 exams have exactly the same difficulties. Right? So their true mean value are actually the same with each other. And then we can consider the exact same thing in terms of different students. So are all these 5 students having the same kind of capability, or same capability, which means that their mean values are all the same, or at least one of them has a significantly better or worse kind of capabilities than the other. Okay, So this is a basic setting that we consider in this two-way ANOVA. And then we can enumerate these observations in this manner. So x11 and x1n. So this belongs to the first group, right? And then within each student, it has x11 going through xm1, right? So this one was originally, this one was the first aspect that we mainly considered in the one-way ANOVA. But this column-wise aspect is the additional aspect that we now consider. Okay, and then, yeah, there are many different equations here, but they are quite easy. Yeah, quite easy. So, but they are kind of tedious. So, let me just skip those details, but give some high-level explanations about this two-way ANOVA setting. Okay, so in the case of a one-way ANOVA, so let me just go back and then use this example. Suppose the true mean value was maybe 3.6 and 3.6 and 3.6. So this is the null hypothesis, right? And then suppose the true parameter value of the mean value was 3.6, but this guy was maybe 3.8, and this guy was 2.9. So in this case, this is corresponding to alternative hypothesis. But in this case, let's just represent differently these mean values, the true parameter values. So, and how we do it is as follows. So we just take the average between these three values. And then what is the average? Let me use a fake mean that we utilize in our high school. And then plus 0.1, plus 0.3, and minus 0.6, and then minus 0.6, minus 0.2 divided by 3. Okay, unfortunately, it doesn't have a clear, a simple number, but let me just re-represent it in this manner. So 3.5, suppose the mean value of these three values were 3.5, and then this value was 0.1 higher or greater, and then this value was 3.5 plus 0.3, and then this guy is 3.5 minus 0.4. So in this case, their global mean will be 0.5, 3.5, right? Okay, so in this case, what is our null hypothesis? What is our null hypothesis? So in this case, let's call this guy as mu, and then this guy as maybe alpha 1, and this guy is mu plus alpha 2, and mu plus alpha 3. So our null hypothesis is now re-represented as this form, right? Okay, so so this is a kind of a special case. So when representing each of the mean of each of these groups, right? And then in general, these values could be like non-zero values when the null hypothesis is not true. Okay, so having that in mind, in the case of two-way ANOVA, we extend this model in this manner. So we had maybe 3 exams, exam 1, exam 2, exam 3, and then maybe student 1, student 2, student 3, student 4. And in this case, we can think of the true parameter, true mean value of this cell. Okay, so this cell. So this cell can be represented as the global mean value of mu, something like 3.5, and then plus alpha 1. But this alpha 1 is coming from this E1. But now, yeah, so this one is just the exact same kind of, yeah, aspect that we considered in the first one-way ANOVA, but we now consider the two-way ANOVA, which means these different students will have their own effect, right, on this mean value. And so that value, let's represent it as beta. So in that case, the mean value can be represented in this form: mu plus alpha 1 plus beta 1. So the mean value of this cell is actually starting from 3.5, but increased by this amount due to this first exam's difficulty, and then also increased by this amount of beta 1 because of the student's capability of the first student. Okay, and then what about this cell? This cell will have the mean value of 3.5 plus alpha 1, right, plus student 2's capability of beta 2. Okay, so we can represent the true mean value. So the true mean value of each different combinations of students and exams. Okay, and then in this model, or in this assumption, okay, in this assumption, is it general enough to cover all the possible cases? So yeah, question doesn't sound, yeah, may not sound clear, but yeah, can we represent any cases in this form? Okay, so let me give an example. So the answer is no, because, so yeah, alpha 1 was 0.1, which means that, yeah, so this is an average score of this exam. So plus 0.1 means that E1 was a little bit easy, right? Because it increased the average kind of, score value by 0.1, and then this student is actually, yeah, not doing great. So this guy is not very smart. So beta 1 was minus 0.2, right? In this case, this student was not very good. So that way, the average value was decreased. Okay, and then the second, let's consider the second exam, and the effect of this, the second exam was actually minus 0.3. So it means this exam was really difficult. So it decreased the average score value by this amount, right? And then, okay, and then what should be the average, I mean the true parameter of the mean value corresponding to this cell? So we already computed this 3.5 is fixed, and then now we have to apply the second exam's effect, right? And then also we have to apply the first student's effect of beta 1. So that means minus 0.3, which means that the second exam was difficult by this particular amount, and then this guy was already fixed in the first model, or the first cell. And so in this manner, so the average, I mean the true mean value of this cell should be 3.0, right? Okay, but what if the true parameter value corresponding to this cell was actually 3.6, okay, which is actually a lot higher than this value, right? So it can, yeah, it is possible as well. I mean, in some cases, right? So how can we interpret that? I mean, what kind of situation may be corresponding to that kind of case? So this student was not a great student, so he or she is not a great student. And then this exam was really difficult, right? But sometimes, or in some cases, this stupid student actually spent a lot of time on the subject that is covered by the second exam. So the first exam was covering chapter 1, okay, but the second exam was covering chapter 2. And then somehow this student was spending a lot of time in studying the chapter 2. In that case, the true mean value of this cell can be higher than just this model, right? So from this, what is the difference? It is 0.6. And then where did this 0.6 come from? This one came from the fact that this kind of a combination of this particular student and that particular exam, right? And then that is called, so that is called what? What is it called? What is the name of it? So this effect or this kind of value is called interaction. So interaction between the first student and the second exam. Okay. So that is corresponding to some measure that is not explained by our model of this form. Okay. So that is kind of two-way ANOVA with interaction. So it is a kind of a high-level overview about what we will study in this chapter. And once you understand how to perform the hypothesis testing in these two kind of scenarios, I mean, in this kind of general scenarios of involving this interaction, and then that will be done for today's class. Okay. But this is a kind of high-level big picture. And then in Korean, you can understand it as 이거를 뭔가 궁합이라는 요소를 좀 생각을 해볼 수도 있어요. 궁합. 그러니까 저 스튜던트와 요 이그잼이 이렇게 같이 합쳐졌을 때 얘네들이 각각 갖고 있던 어떤 요소들 이외에 뭔가 시너지를 낼 수도 있고요. 혹은 궁합이 안 맞으면 완전 후 이렇게 될 수 있죠. 그러니까 시너지의 반대가 뭘까요? 뭐 있을 텐데 뭐 하여튼 뭐 하여튼 뭐 그런 거. 네. Okay, so if our model in this setting, if our model doesn't have any interaction effect, so all the mean values corresponding to each of these cells are fully represented by this this form, and then we call it, or we call this problem setting as a kind of additive kind of nature. Our model is additive, which means that the mean value is represented fully represented by just adding individual kind of individual effect of these aspects that we have. Okay, so any questions so far? Okay, and then let me now introduce one really important characteristic that we will keep utilizing. Okay, so that aspect is as follows. So in this case, so our mean value was 3.6 and 3.8, and so in this case it should be 3.1, right? So these were our original kind of values, and then we just re-represented it in different manner by introducing this mu and the difference with respect to the mu as alpha 1, alpha 2, alpha 3. And then how did we set, or how did we determine this mu? So it was determined as the global average of the true values of 3.6, 3.8, and 3.1, right? And what does that mean? or from this, from the from this way of setting the mu value, okay, so we can always obtain this kind of equation of alpha I, or simply alpha 1, alpha 2, alpha 3 should be 1. It should be always 0, right? Because we set this mu value so that it is equal to the global mean of these three values. So their differences and their sum of these differences should always be 0, right? Okay, so back to this 2A setting. If our model is fully represented by this additive model, okay, in this additive model, how do we set this mu? Mu is set as the average value of all these true parameter values, okay, all the true parameter values, and then take the average of them, and then we set it as mu, okay. In that case, so we will have alpha 1, alpha 2, alpha 1 and alpha 2 and alpha 3, and then the summation of alpha i's should be 0, because we set our mu values as a global mean value. Although I will not prove it, because the proof is really a straightforward extension from what we learned, or from this simple example. So it's just an extension of this guy into like a two-dimensional kind of matrix case. But this one comes from, it is important to note that, or keep this in mind, that this sum of alpha i's are equal to 0, and then likewise sum of beta i's are equal to 0. Okay. Okay, so let's keep that in mind, and then let's go to the details about this 2A ANOVA setting. So you see these equations, right, that we just described, but the book is showing a little bit tedious settings about why this one should be true. Yep, so this is a useful fact that I just emphasized, right? So when summing of alpha i's and also summing of beta i's are all generating zeros. Okay, and then and then now let's think of the estimator for our true parameter of mu and alpha i's and beta j's in this case. So so back to see. Let's see. Okay, so let's get back to this example. So in practice, of course, we do not know the true parameter of mu and alpha I, alpha 2, and alpha 3, right? So how do we estimate them? How do we estimate this 3.6 and 3.8 and 2.9 or 3.1? So these are the true parameter, right? So we considered, or we view them as the true parameters. So true parameter really exists, but we do not know what the exact values are. But we estimate them and use them instead, right? And then how do we estimate them? For this 3.6, we actually take the average between them, and then this value could be 3.7, but this one can be different from the true parameter. But we use this guy as an estimator for this 3.6, and then by using this guy, instead of using this guy, So it actually has the effect, or it plays a role of decreasing the degree of freedom by 1, right? So that was the effect of it, right? Okay, but this guy was actually the estimator of this value. And then now when representing this 3.6 in this form, we can now represent the estimator, or we can now compute the estimator for mu1 and alpha 1. Okay, so again, we are obtaining the estimator for this new representation for this mu and alpha 1. And then how do we estimate this mu? How do we obtain the estimator for this mu? We just simply take the average of all these guys. Okay, so that was what? So that was represented as x dot dot, right? And then what about this alpha 1? Alpha 1. Okay, so in this case, we suppose we took the average and obtained this guy. And then what was the representation of it? It was x1 dot, right? And then how can we obtain this alpha 1? I mean estimator for alpha 1. We can just simply use this value minus x dot dot, right? The difference of this sample mean of the first group from the global mean. So we can use that as an estimator for this alpha 1. And then also we can use this alpha 2 in the same manner, x2 dot minus x dot dot, right? Okay, so that's how we obtain this estimator for alphas, or alpha 1, 2, and 3, and mu, right? And then let's come back to this 2A setting, and then how we obtain the estimator for mu and alpha 1 and alpha 2 and alpha 3, and also beta 1 and beta 2 and beta 3. So it is really a simple extension. Okay, so from here, so we can obtain the estimator for the global mean, which can be now represented as mu hat. Yeah, hat means estimator of this true parameter, right? And then we use it as x dot dot, right? And then what is alpha 1? So alpha 1 is, so this one is corresponding to alpha 1. So so alpha 2 and so on. So these are some increase or decrease from this global mean due to the first effect, or the first exam and second and the third exam and so on, right? And then how do you obtain this alpha 1? If you remember what we just did in the previous example, we obtain the sample mean of the first group due to this first effect. And so it is called x1 dot still, right? And then minus x dot dot. So this one is our effect of an alpha 1. Okay? We actually did exactly the same thing. But now we do this thing on this vertical factor, or the student factor, right? And so we take the average of these, and then what is the, how do you represent it? It is x dot 1, right? And then minus x dot dot. What is this? I mean, what kind of estimator is this? It is the estimator for beta 1, which is corresponding to like the capability of the first student, right? Okay, so we now obtained the estimator for the true parameter or true global mean value of mu, and then beta 1, and estimator for beta 1 and estimator for alpha 1. And in this case, still similar to the fact that alpha i's were summing up to 0, and their estimator alpha i's hat will be summing up to 0. Okay, so I will not prove it, but again, the proof is really kind of simple. But you can follow, if you want, you can follow all these like these kind of equations. but these are, yeah, quite easy, and yeah, although it is a little bit lengthy, but you can follow these proofs. But yeah, please note that, or please remember that, similar to the true parameters of this alpha i's, and their sum being 0, their estimator and then summing up these estimators will result in also zeros. Okay. Yeah, and that is because this alpha i's, this estimator for alpha i's and beta i's are actually the unbiased estimator for the true parameter alpha I and beta i's. Yeah, but yeah, that is a little bit more detail, but you can get, yeah, it is just enough to get this kind of a high level kind of understanding about about this kind of characteristic. Okay, and then you guys now understand these, right? Mu hat, estimator for mu, which is represented as mu hat, is used by this, and so on. Okay, so let's look at this example. So student and exam, and then we sum up row wise and the column wise, and then take the average by dividing it by 4 and dividing it by 5 and so on, and that way we obtain xi dot or x dot j. Okay, and then we obtain this, which is the global total, or the total sum of all these values, and then divide it by 4 times 5. Okay, and that way we obtain the estimate of the global mean value, which is represented as x dot dot. Okay, and then we now obtain the estimator for alpha i's and beta j's in this manner. Okay, it's really simple. So for this guy, we subtract from this value by this value. So 2.5 is the capability of this first student, okay, compared to the average kind of capability. Any questions so far? Yes, I believe it's yeah. So far it is easy, right? Okay, and then now let's go to the main task of hypothesis testing. So the hypothesis testing in this two-way ANOVA can be like in two different forms. The first hypothesis is this guy. All alpha i's are 0. Okay, so this is the null hypothesis, and then the converse or the opposite case where at least one of them is different from the rest. Okay, so that is alternative hypothesis, and this is just the exact same hypothesis that we used in the one-way ANOVA, right? So in the previous case, like a mu1, mu2, so this was the null hypothesis again, but this exact same meaning is now represented as alpha 1, alpha 2 being all equal to 0, right? So this is just a different kind of representation, but exactly the same meaning. Okay, so this is the first hypothesis testing. I mean the first setting that we consider, and then another separate hypothesis setting that we test is this one. All beta i's are equal to 0. Okay, so in the first case, our different exams have really the true mean value, or they have the exact same difficulties. And that is the first hypothesis. And the second hypothesis is we don't care about the difficulty, whether the exams are different or not. I mean, in terms of their difficulties, but we only care about the students' capability. So the question is, are the students' capabilities are different from each other, or they are all the same? So we do not care about alpha i's, but only care about beta j's in the second setting. Okay. And then if we know how to perform this the first case, and then the second one will be just a trivial, right? Because we will just use the exact same kind of strategy of doing the hypothesis testing in the second case. Okay, and then now we utilize still the same strategy. So we apply like two different ways of estimating sigma squared. Okay, so still in the one-way and also the two-way ANOVA, the common hypothesis, or the hypothesis that we still assuming in all the cases, is that the sigmas are the same. So even though, or even if their means may be different or may be the same, but their sigma or variances are always the same. So that is the assumption that we used across all the different problem sets, or actually throughout the entire chapter 10. So we always assume that sigma squared are the same, okay, between different groups or different students. Okay. Okay, but yeah. So back to the main strategy. We again, I mentioned that we will just use two different ways of computing the estimate of sigma squared. Okay. So let's consider the first way. Okay. So the first way was valid regardless of whether the null hypothesis is true or not, right? So that was corresponding to this SS of W, right? Okay, so let's consider SS of W. Okay, so Xij that we actually obtained as our observation, and then we just simply subtract its corresponding mean value and take the square of it, and then divide it by its common sigma squared, and then it will form the chi-square distribution, right? And then what is this mean value of this guy? So we have to use the true mean value in the first place, and so the true mean value is represented in this form, right? Mu plus alpha I plus beta j, right? Okay, so if we were to use the true parameters, and then what is the degree of freedom? It is still m times n, right? So the only difference is that we used its corresponding mean, which has a little bit more complicated form than compared to the one-way ANOVA setting. Okay. Okay, and then now the next step was to replace the true parameter. I mean, these parameters are unknown, so we replace them with the approximate estimator that we obtained for these, right? So we plug in our estimator for mu and alpha I and beta j. Okay, so that is the first step, and then that will cause the decrease in the degree of freedom. And the question is, how much the degree of freedom is decreased? Okay. Okay, so we now represent our true mean values by using approximate estimator, right? And then so in this case, it is a little bit tricky, and yeah, you have to kind of understand it only intuitively. I mean, not rigorously, but let's just let's just follow the logic that is shown in this book. So how much degree of freedom should be decreased? So that is our main question here. Okay. So let's start with the mu, and then replacing it by our estimator for global mean. So that will correspond to one parameter estimation, or one kind of degree of freedom that we have to decrease. Okay, and then how many alpha values do we have? Alpha values, in the case of this 4 different exams, m was 4 and n was 5. So in the case of an alpha, the degree of freedom, parameter that we have to estimate is actually 4, right? And then so far we used estimator for this global mean, and then also there's 4 different alpha values, right? So we used in total 5 different estimator. Does it make sense, right? And then in general, it will decrease the degree of freedom by 5, right? But is it really 5? Is it really 5? Is it really 5? So let's just recall just one-way ANOVA. Just one-way ANOVA. In the one-way ANOVA, instead of using this kind of setting, mu plus alpha 1, alpha 2, and so on, we actually just used it as mu 1 and mu 2 and so on, right? So in that case, how many mu's do we have? Mu 1, mu 2, and mu 3, and mu 4. So we only have 4 parameters. And then now we just represented them as mu plus alpha 1, mu plus alpha 2, mu plus alpha 3, and so on. So now suddenly we now have 5 different parameters, right? In the exact same setting, right? So why do we see this different number of parameters? Okay. So here, so the trick or the one kind of key thing that we have to focus on is, even though it looks like 5 different parameters of single mu and alpha 1, alpha 2, alpha 3, and alpha 4, but they are actually not 5 different numbers. They are actually 4 different numbers, because among these 4 values of alpha 1, alpha 2, and alpha 3, and alpha 4, they should always satisfy this equation, right? So suppose you obtained the estimator for alpha 1, 2, 3, and then the estimator for alpha 4 is automatically determined. Okay, so it is not something that we actually estimate, but it is just automatically determined by other values. Okay, so that way, still the degree of freedom that we should decrease is still the 4, not 5, because we are actually estimating 4 different parameters. Although, and at the same time, the 5th parameter of alpha 4 is just automatically determined, not something that we actually estimate. Okay, so that is the key thing, and that's why we have to focus on this kind of where is it? That's why we have to keep this equation in mind. So this equation will have the effect of actually removing one actual parameter estimation. Okay. Okay. So any questions so far? I think it's a really important part. So the rest of them, should be just easy by just applying the exact same principles over and over. Okay, so let's take some break of maybe 10-minute break. Then I'll resume on 8:25, 8:22. Okay. No, 7:22. Sorry, 7:22. We will resume our class.
여기서
네.
네. 테스트하는데 그
네.
1차 추정량과 2차 추정량을 보면서 그 비를 쓴 거잖아요.
네.
원래 얘는 그 얘가 참이면 둘 다 시그마 제곱을 가까이 내면 약간 1에 가까워져.
네, 그렇죠.
근데 그러면 얘네를 유도할 때
네.
그 이 가설이 참이 아니라는 거를, 그러니까 얘는
네.
가설이 참이라고 가정을 하고 하는 거잖아요.
네.
그거에 해당하는 그 조건이 뭐죠?
아, 그러니까 이제 이게 SSW를 이거를 쓸 때가 이제 항상 크기가 더 작고 얘가 더 크잖아요. 그러니까 왜냐하면 이거는 가설, 그러니까 널 가설이 맞든 틀리든 만족이 되는 어떤 그런 에스티메이터고, 이거는 널 가설이 맞을 때만 이게 되는 거고, 널 가설이 만약에 틀리면 이건 이제 틀렸으니까 이렇게 했을 때는 그 실제 시그마 스퀘어보다 훨씬 큰 값을 이렇게 내줄 거라는 거죠.
아,
이해가요?
그러니까 틀릴 가능성이 있기 때문에 얘가 무조건 크게 나와요. 그러니까 더
네.
과대하는 걸 하는 경우가 있어요.
네. 시그마가 만약에 5 정도 됐다 그러면, 시그마가 실제로는 5예요. 5의 제곱 25다 그러면 얘는 5 주변으로 이제 그 에스티메이터를 줄 거란 말이죠. 5의 제곱의 주변으로. 그 다음에 얘는 이제 널 가설이 만약에 맞다면 얘도 이제 언바이어스드 에스티메이터이기 때문에, 널 가설이 맞다면 그러면 이제 5의 제곱을 근처로 값을 줄 텐데, 실제로 널 가설이 만약에 틀렸다면 이 값은 이제 훨씬 더 큰 값을 줄 거라는 거죠. 왜냐하면 글로벌 민을 얘는 썼는데, 그 글로벌 민을 다 똑같이 쓴다라는 말은 그룹마다의 그 평균값이 같으면 이렇게 해도 상관없는데, 같지 않으면은 글로벌 민을 썼을 때는 실제 각각이 갖고 있는 민을 쓰는 대신에, 그러면 이 값이 실제 시그마 스퀘어라는 정해진 어떤, 우리는 모르지만 정해진 값보다 더 이제 뭔가 크게 나타날 거잖아요. 그래서 이게 일반적으로는 이거보다 더, 이게 항상 이제 이거보다 좀 크게 나옵니다.
항상이요.
네. 그래서 이제 이 비율이, 그래서 이제 우리가 이거를 이제 원 사이디드 테스트를 하는 이유도 네, 이게 이제 두 개 카이 스퀘어 두 개 비율이기 때문에 우리는 F 디스트리뷰션을 쓰는데 중요한 게 이제 여기서 이제 원 사이디드 테스트를 써요. 그러니까 얘가 뭐 얘보다 더 작아질 일은 없다라고 생각하기 때문에.
그럼요. 그 저희가 지금 가설 검정을 2A에서만 하잖아요.
2A에서
네, 그러니까 따로 단어를 만든 거는 2A에서 단어를 만든
네네네.
거는 그냥 하나의 요인만 나와도 그냥 이거 2A로 생각하고 이 가설을 검정하면서 하는.
맞아요, 예, 맞아요.
그럼 만약 가설이 채택이 되면 그냥 1A로 보는 거 그런 거.
2A에서를 가정을 해도요. 2A에서 해도 그러니까 원웨이랑 그냥 똑같은 방식으로 이제 한다는 거거든요.
네.
네.
그러니까 그냥 데이터 집합이 주어지면
네.
일단 두 개의 가설을 검정을 하는 걸로 생각하면 돼요.
이 2A는 이제 그러니까 하여튼 그 가로축의 이펙트와 세로축의 이펙트 요게 잘 이렇게 얼라인이 되어 잘 이렇게 뭔가 정렬이 되어 있는 테이블이 존재하는 이런 상황에서 우리가 가정을 하는 거고 거기서 이러한 이제 테스팅을 하는 거죠. 가설 검정. 네. 시험들 많이 보나요? 많죠? 네? 그래요? 아, 그렇군요. 네. 무슨 과목이요? 네? 아, 잘 표현하면 되겠네요. 오늘 뭐 배워요, 그러면? 어떤 잘 표현하는 거 배워요?
컴퓨터 전반적인 왜 우리가 공부를 해야 되나?
네?
왜 컴퓨터를 공부해야 되나?
먹고 살려고 하는 거죠, 뭐. 왜 공부했는데, 그래서?
늘 효율적으로 하려면
어. 그게 전공 뭔가 필수 과목이에요, 그러면?
그냥
아, 교양? 아, 그렇군요.
스팅 시트
네.
A4 한 장.
네.
양면.
양면이요? 양면. 그냥 한 명만 해도 되지 않을까요? 양면. 아니, 내가 옛날에 이런 적이 있었어요. 치팅식을 얘기했나? 그 친구들이 별로 공부를 열심히 안 하던 친구들이 많았는데 공부는 하나도 안 하고 치팅식만 죽어라 작성해갖고 정말 빽빽하게 밤새 작성한 거예요. 치팅식 하나 만드는 것도 시간이 굉장히 오래 걸리잖아요. 꼼꼼하게 다 쓰려고 거의 책을 거의 필사를 할 정도로. 네, 그래서 하여튼 그 다음 시험 직전에 애들이 다 그걸 복사를 해갖고 썼죠. 네, 걔가 좀 되게 허무해하더라고. 뭐 포인트는 너무 많이 써도 그것도 참 본인 스스로 좀 괴롭지 않을까. 여기 선택과 집중의 문제, 뭔가 이해를 해서 내가 뭔가 응용력이나 이런 좀 지식의 깊이를 내가 추가했느냐, 아니면 뭔가 이걸 내가 암기 전략으로다가 드립다 공식을 이렇게 해갖고 할 것이냐. 네, 그래요. 그럼 해서 마무리를 짓죠. 다들 바쁠 텐데. Okay, so let's continue. So back to so the thing that I mentioned was this guy. So in this case, so if we had a 4 different parameters, which is just an initial or the original setting that we first considered, in this case, like mu1, mu2, and mu3, and mu4, and then these 4 is actually the amount of the degree of freedom that we have to decrease, right? Because we actually, if you just recall, if we just recall this kind of equation, okay, instead of this mu1, we replaced it as it's a sample mean. So that has an effect of decreasing the degree of freedom by 1, right? So we have like in this example, 4 different groups, and we actually reduce the degree of freedom by 4, and then that 4 is the same number, the same as the number of parameters that we have to estimate, right? Okay, so that way we can think of this number of parameters that we have to estimate as the same as the number of degree of freedom that we have to decrease from our chi-square distribution, right? So that is a important insight, or kind of characteristic that we have to keep in mind. So so let's just consider how many parameters we have to estimate in this two-way ANOVA setting. Okay, now we have one global mean value mu, right? And then in this case, alpha i's were like in the previous case 1 plus 4 different alpha i's, right? We had 4 different groups, but in this case it's actually 3 parameters, because the last one is automatically determined by this equation. Where is it? This equation. Okay, and then what about the betas? Okay, betas are, in this case, we have 5 different betas. And also the betas should be, beta j's should be summing up to 0. And so the number of actual parameters that we have to estimate is n minus 1, or 4 different parameters. Okay, so overall in this two-way ANOVA setting, how many parameters should we estimate? The global one, and then in this case m was 4, and so 3, and n was 5, and so 4. So altogether 8 is the total number of parameters that we have to actually estimate, and that is the number, the same as the number of degree of freedom that we have to decrease. Okay, and then let's just represent it by using the notation of m and n. So 1, which is corresponding to mu, and m minus 1 and n minus 1. Okay, so these are the actual number of parameters that we have to estimate. And so altogether, this one is the number of parameters, and then this is something that we have to decrease by this amount, right? And so again, the total, originally the total number of total degree of freedom was m times n, right? When just using the true parameters, right? And then we have to subtract this amount, right? Because this is the number of parameters that we have to estimate. And then after doing some simple factorization, we obtain this degree of freedom for this estimator for the first kind of a way of computing the estimate of sigma squared. Okay, and then what was a mu hat? It's corresponding to this guy. Okay, x dot dot. This guy is, yeah, so mu hat was this, and this guy was this, and this guy was this, right? And so if we sum them up, and then one of them is cancelled out, right? And so summing up all together, then this representation is actually the same as this representation. Okay, so this is our something similar to SSW, but in this two-way ANOVA setting, it is called SSE, and that is called the error sum of squares. Okay. Yeah, I don't know if that is a good name or not, but but that is an official name for this term. Okay, and then this one is having the degree is following the chi-square distribution when divided by sigma squared, and then the degree of freedom is this guy, and then we do exactly the same trick, and then we move it to the denominator here, and then it will give the estimate of sigma squared, and then this guy is an unbiased estimator for sigma squared. Okay, and then now we have to think about we have to think about the second way of computing the sigma squared, right? Okay, so It is actually exactly the same as the one-way ANOVA setting in the case of when handling alpha i's, right? So we consider the sample mean from each group. So in this case, see, yeah, we compute the sample mean of this guy, which is xi dot, and then minus mu, and then divided by what? Square root of sigma squared divided by 5, right? So that is corresponding to the standard Gaussian random variable. Okay, then we have 4 different groups. So yep, so this guy. So this one was coming from here, right? And then this guy, where we replace the global mean value as our estimator, x dot dot. And then that is chi-square distribution with the degree of freedom of what? M. But we have one less degree of freedom, right? Yep, so it's yeah, literally like exactly the same as one-way ANOVA setting. In the case of computing, the estimate of the sigma squared in the by using the second method. Okay, so here in the two-way ANOVA, because we are considering 2 different aspects, so the row effect or the column effect. So instead of calling it as SS of B, we just call it as SS of R. And then likewise, so R is standing for row, and then yeah, likewise we can compute SS of C or column wise, yeah, right? Okay, and then the hypothesis testing is now quite easy. So in the numerator, yeah, we utilize this guy, the second way of computing sigma squared, and then the denominator was yeah, this guy, right? And so yeah, we obtain the degree of freedom in this manner, right? So this is the key part, and so that is forming our denominator for our test statistic. So this is the hypothesis testing for the row effect, whether the alpha i's are all 0 or at least one of them is not 0. And it's following the chi-squared, the F distribution with the degree of freedom of m-1 and this value of degree of freedom coming from the denominator, right? So it's quite easy, right? Okay, so the book is skipping the case of the hypothesis testing in the case for the column effect, but the column effect should be easily extended by using the row effect one. Yep. So so here in order to compute the test statistic, we compute SS of R, SS of C, SS of E, which is corresponding to something like SS of W, and these are corresponding to SSB or something like that, right? But the degree of freedom is m-1, but in the case of row-wise manner, it will have the degree of freedom of n-1 because we have a 5 student, and then their degree of freedom will be 5 minus 1, right? Yeah, because we simply have 5 different columns. Okay, then yeah. So this is the first setting where the additive model is assumed. Okay, so here we didn't consider any interaction term, right? But if our model is following this additive model, and then this is the ANOVA testing that we can perform. Any questions so far? Yeah, I believe you guys should be able to follow this example easily. And, so it's just a matter of computing these statistics and then compute this measure and then look at the F distribution with the corresponding degree of freedom right? With the n-1. Oh, yeah, here. Yeah, there is a one notation introduced here. So what was the degree of freedom of this SS of E? So this one was, yeah, again, this guy, right? So this guy is probably one of the most important parts in this class, right? Today's class, right? And so it is represented in this manner, and then we just call it as large N. Okay, so this is just a notation that we introduced here. So N is defined in this manner, and then the second parameter or second degree of freedom of our F distribution is defined in this manner. Any questions so far? Okay, now it's the last piece, last part of our chapter 10, which is about this two-way ANOVA extended to like the case of considering interaction. Okay, interaction. Okay, so I think yeah, you guys have already a good idea about the problem setting when our two-way ANOVA is involving this interaction term. So yeah, remember the example that I showed here. Okay, so when following the additive model, okay, when alpha 1 and alpha 2, for example, alpha 2 and beta 1 corresponding to this this cell, okay, alpha 2 was minus 0.3 and minus 0.2, and then when summing them up, this value should be 3.0, but their actual mean value was found to be 3.6, right? The difference between this actual mean value, I mean, we are talking about the true parameter value, right? True parameter, and then this is the actual value, and this value is coming from the additive model, right? Which is just a global mean, and then adding the effect of these two individual kind of effect from the first factor and the second factor. Okay. Okay, so if you keep that in mind, and then it should be easy to follow. So let's where is it? Yep. So far, when computing mu, which is global mean, and alpha i's and beta j's are exactly the same. Okay, but our actual mean, which was something like 3.6, is this value, and then this guy is 3.5, and this guy was what? Minus 0.2 or 3, right? What was that? Oops. Okay, minus 0.3 and minus 0.2. Oops. Okay, minus 0.3. Uh-oh, yeah. So this guy is 3.5, and this guy is minus 0.3, and this guy is minus 0.2, right? By using the previous example. So this is a global score, and then this guy is the maybe first, it was second exam, yeah, second exam's difficulty, and then this guy is the first, like a student, this particular student's effect, right? But this student did really well unexpectedly, right? For this particular exam, because he or she studied a lot on this chapter 2, maybe. And that way, the actual average score or actual mean value was 3.6, right? And then this guy, this value comes from the additive model, and then when taking the difference between them, okay, so this value is 0.6, and this guy is called our interaction term, right? 예. So 그러니까 궁합이라고 하는 게 여기서 이제 감마라고 하는 걸로 나타내지는 거예요. Okay, so gamma ij is a kind of matching, okay, or harmony between i's exam and j's student. Okay, so now we have a fully general model, right? So we can model by using this. We can model any kind of general kind of cases. Okay, so again here the true mean parameter for ICE exam and J student is represented in this manner. So mu is a global mean value, and it's a ICE exams effect and J students effect, and this is an interaction effect when matching ICE exam with the J student, right? But what about these representations? These representations are just focusing on the what is the differences. Okay, what is the differences? So here, so still, from the fact that this guy is like a global mean value coming from like the mu1, mu2, and mu3, and mu4, we just take the average of these true parameter, and that's how we compute the mu, the true parameter mu, right? So that way, again, this is satisfied, right? And then this guy is satisfied, and then also gamma ij should also be satisfied in this manner. Okay, so if it was not satisfied, for example, like if it was 1, okay, and then we can simply make it as 0, and then move that offset value to this global mean. I mean, it's just a conceptual explanation, but anyways, it should be satisfied all the time. And in more detail, what is this guy? What is this guy? So if we had 4 different exams and maybe 3 different students. So in this case, we will have the interaction term of gamma 11, gamma 12, gamma 13, gamma 21, and so on, right? So not just the summation of all these gammas should be 0, okay, but also the row-wise sum of these gammas should be 0, okay, and also column-wise should also be 0, okay. So that is also always satisfied when computing this mu mu in this manner, okay, taking the global average of the true mean values from all the cells, okay. Okay, so this is the important kind of characteristic that these parameters should satisfy. And why is this characteristic important? Because that determines the number of degrees of freedom that we have, the number of amount that we have to decrease from our original degree of freedom, right? So the overall story still will still be the same. Okay, so mathematically, alpha is their sum is 0, beta is, and also gamma ij when fixing j's and then either iterating or summing up over all gamma i's, and then it will be 0. So when j is fixed as 1, for example, in this case j is fixed as 1, right? And then the summation of this gamma over i's, I1, I2, I3, and I4. So these yellow part will be equal to 0. Okay, then row-wise and the column-wise sum will be 0 of this for this gamma. Okay, so let's see. And then now, when considering this interaction term, we actually think of some a little bit more complicated or extended setting in this case. So Yeah, I don't know why exactly, but the main problem setting or main observations that we have has this form. So yeah, let's go back to this test and exam case. Where was it? Yeah, so in this case, for particular student and particular exam, how many observations do we have? Only one, corresponding to each cell, right? But what about this? What about this situation where each cell has multiple observations? Okay, multiple observations. So that actually makes it kind of meaningful to consider the interaction term. Okay, so yeah, I cannot explain properly. I mean, I cannot explain kind of well about why we have to consider this situation. But let's just consider this situation as a kind of a more general case, right? So not just one sample, we have not just one observation, we have multiple observations within each cell in this case. So we can still, we can easily think of such kind of example in this case. So suppose we have like, so the first effect is maybe male or female. So we have these two factors. Okay, and then this guy is Korea, and then maybe United States. Okay, in this case, male and Korea, and then their corresponding cell, and each cell will likely contain many observations, right? So we can consider still this kind of situation, and then this is the main kind of a problem setting or data set that we consider in this two-way ANOVA with interaction. And also in this case, by default, we consider that the number of observations within each cell is all the same. Okay, so we have M. Okay, so we have M different groups, right? And then also N different groups as well, column-wise. So M times N, and also within each cell, we assume that L different samples, M and L. Okay, so in this special case, L was 1, but when considering the interaction, L can be like a multiple number or larger than 1. Okay, so in this setting, so now we have the triple indices I, J, and K. What does that mean? So if I was 1 and if I was 2, J was 1, and then this is a second exam and the first student, and then this guy is like index of an observation within that particular set, right? So K can go from 1 through L. Okay, and then what does that follow? So now we have to utilize the exact same way of computing the estimate of the sigma squared in two different ways. So now let's first consider like the first way of computing sigma squared. And so this guy is following this Gaussian distribution where we still have a common or the exact same variance as well. And then also the mean value will be represented in this manner, right? Because that was our original assumption that we started with here, right? So mu ij is represented as this additive model and then interaction term. Okay, so if we knew all these parameters, and then it will follow this Gaussian distribution with this mean and this variance. Okay, and then now we think of like 3 different hypothesis testing. So the first hypothesis, the first null hypothesis that we consider is this guy. The effect of the rows or the exams are 0. Okay, so which means all these alpha i's are 0. And separately, so this hypothesis testing is done against H alpha or alternative hypothesis, right? Which is at least one of them is not zero. So this is one separate hypothesis testing that we consider. And then the second separate hypothesis testing that we consider is this guy. Column-wise effect has no effect, right? And then versus like, at least one of them is not zero. And then the third hypothesis that we consider here is this guy. Whether these interaction terms are all zeros, which means in this cell, like for example, like in this cell, so they are fully represented as just an additive model, okay? And then in that case, no interaction term. I mean, interaction term will be all zeros in every different every cells, okay? So this is the null hypothesis about our interaction term, and at least one of them is not zero. So this is the null hypothesis. Alternative hypothesis against this the third case. Okay, and then now let's consider this measure, xijk. Okay, so yeah, let's just consider this situation. So male versus female, and then maybe Korea and Japan, and then US. And then we collected maybe 10 different observations. Okay, and then M is 2, and N is 3, and L is 10 in this case. And then in terms of estimating sigma squared by using the first approach, we have this measure. So if I was 1, J was 2, and K was maybe 5, and then corresponding to this cell, we will have 10 different observations, and then we obtain the 5th observation within that cell. So that is the meaning of this guy. And then this guy has the mean value, the true mean, as sigma mu plus alpha I plus beta j plus this interaction term, right? Okay, when constructing this, then it will follow the chi-square distribution with degree of freedom of m and l, right? So in this case, each cell contains 10 observations. So in total, we have 3 times 10. In total, 60 samples. So this is the degree of freedom. Okay. And then now, what is the next step? We have to replace these true parameters with our estimator, and then that will reduce or decrease our degree of freedom by a certain amount, right? Okay, so we just replace them by using our estimator. And then how do you obtain this estimator? Let me see. Okay, so yeah, it is shown here. So mu hat, or the estimator for mu, is just simply global mean, which means we just simply take the average of all these 60 observations, right? And then what about beta hat and alpha hat? For the alpha 1 hat, okay, so in this case, what is alpha 1? It is corresponding to this guy, and then we consider the sample mean of these guys, right? So how many samples do we have? 3 times 10. So 30 different observations, and take the average of them, right? And that is represented by xi, in this case x1 dot dot, right? Minus what? Global mean, because we are considering the difference from the true mean. The global mean, right? It's quite easy, right? And then also similarly, we can obtain this estimate of this beta hat, right? And then what about this interaction term? What about this interaction term? So in the case of an interaction term corresponding to here, then we compute the sample mean of this corresponding cell. So 10 different observations, and take the average of these 10 different samples. So that can be represented as x 2 comma, in this case 2 comma 2 and dot, right? Okay, and then that is represented by this guy, and then we now also have this mean value computed from our additive model, right? Mu hat plus this beta alpha I plus beta j, and their estimators, right? And that way we can obtain this interaction term, estimator for this interaction term, right? Okay, and then we replace these values in the place of the true parameters. Mu and alpha I, beta j, and gamma ij. And then now we have to think about the number of parameters, number of actual parameters that we have to estimate. So that will be the number of degree of freedom that we have to reduce by. Okay, so let's consider it. So this guy is corresponding to mu. So we now compute this number of degrees of freedom to decrease. Okay, so this is the amount of decrease. Okay, so this is corresponding to mu, and then we compute. We have to estimate alpha i's, but like what we saw in the previous slides, it is actually having the number of m minus 1, because alpha sum over alpha i's should be 0, right? And then n minus 1 is corresponding to like beta j's, right? And then what about this interaction term? So in total, how many interaction terms do we have? So in this case we have 2, 3. Simply, it's just the total number of cells that we have in this case. 2 times 3, right? So m times n is the total number of parameters for our interaction term, right? But this interaction terms should satisfy this this very, very important equation, right? And then let's just let's just use this table, and then let's just try to estimate them one by one. Okay, so we estimated this value and also this value, and then this guy. What about this guy? This guy is automatically determined, right? So this doesn't contribute to the actual parameter to estimate, right? And then this guy and this guy, and this guy and this guy. Okay, and then we are automatically filling these 3 up. And then what about these 3? Are they filled up automatically? The answer is yes, right? Because this row-wise sum should also be 1, right? And then how many actual parameters do we have in this case? So if we have m times n cells, then it will be m minus 1 times n minus 1 actual number of parameters to estimate, right? Okay, so this is shown here. So in total, this guy is corresponding to alpha, this guy is corresponding to mu, alpha i's, and beta j's, and this guy is gamma I comma j, right? And so altogether, if you just manipulate them and simplify them, and then the total number of parameters will be represented as n times m. Okay, so so again, this guy had originally n times m times l number degree of freedom, and minus n times m, and thus n times m times l minus 1 is the final degree of freedom for this chi-square distribution. Okay. Okay, and then now we have to think about the second scenario, right? The second scenario. So the second scenario, yeah. Okay, so what kind of a hypothesis are we considering in this case? So again, we can consider three different separate set of a hypothesis testing, right? And then the first and the second one, I mean the hypothesis testing for the first and the second hypothesis are actually exactly the same as just the two-way ANOVA with no interaction, so without any interaction. Okay, so if you think of like so in this case, let's consider this case SS of an R. So this equation was exactly the same as just a one-way ANOVA, right? But still, our assumption was like the observation or the samples that we have was following the setting of this kind of two-way ANOVA, like the paired setting, column-wise as well. So column had a certain meaning, which is corresponding to different students, right? Yeah, similarly in this case, even though we consider a little bit more a little bit more general or complicated situation where each cell has 10 different samples. Now we have more than one samples within each cell. But still, when computing the hypothesis testing for like alpha i's or beta i's being all 0 or not, so we still use the exact same hypothesis testing kind of equations, just like the two-way ANOVA with no interaction. And then now the remaining one, the only remaining one is this guy, the hypothesis testing about this interaction part. Okay, so in order to compute or perform this hypothesis testing, so this was the first measure of computing the estimating the sigma squared. And then what about the second way of computing sigma squared? Okay, and then here we consider this guy xij dot. Okay, so again, in this setting, 2 times 3 times, like each cell containing 10 observations. Okay, and then for those guys, so for those 10 different samples, okay, so if we had no interaction terms at all, which means if our null hypothesis was satisfied, so assuming that this guy was true, and then gamma ij's will all be 0, and then now the true mean value for this cell will be just fully represented as an additive model, which is mu plus alpha I plus beta j, right? Okay, so this one is sample mean of 10 different samples or L different samples, and then square root of sigma squared divided by L will be the standard Gaussian random variable, and then L will be here, and then take the square of it, and then summing them up over all the cells. So we have like in total 6 different cells. And so we are considering the sample mean from each different cell. And when computing this measure, what will be the degree of freedom? Degree of freedom will be n times m, because we have 6 different cells. And then we are we are summing up squared random variables from 6 different cells, right? Okay, so again, this is the valid estimator only when the null hypothesis is true, which means this gamma ij's are 0, or interaction terms are all 0. Okay, so it had n times m degree of freedom originally, but the next step that we have to do is to replace these parameters by using our estimator, and that will reduce or decrease our degree of freedom. And then how much degree of freedom will be decreased? So that is our concern, right? And so in this case, we replace them, and then likewise this guy can be represented as x dot dot dot, and this guy, yeah, you can represent it as maybe x I dot dot, right, minus x dot dot dot, right? Okay, so yeah, if you plug these values, and then one of them is cancelled out, and then yeah, this is a kind of similar equation or representation that we saw. And then here, from the original degree of freedom of m times n, and then how much parameters do we actually estimate in this case? Yep. Yeah, so it is really the same as the additive setting or additive model with no interaction. So we already considered it in the previous slide. So mu is just one number of parameters, and alpha i's n minus 1 plus beta j's n minus 1, right? So m plus n plus minus n is the number of actual parameters to estimate, and then m times n minus this value is the final degree of freedom. And then if we factor them out, and then it's like m minus 1 times n minus 1, which is our final degree of freedom, right? Okay, and then finally we can obtain the test statistic for our hypothesis testing for the interaction term being all 0 or not. So we have SS of an E, and then n times m times n minus 1. So here the reason why we see this L is because we are considering like this kind of setting where each cell contains multiple observations, right? And that's why we are introducing this L as additional notations. Yep. So denominator and the numerator, it will follow the F distribution, and then the rest of the scenarios will exactly be the same. So this one comes from here, this one is replaced here. Yep, and then I'll perform this F test, yeah, hypothesis testing by using the random variable of an F. Okay, so yeah, so and then we consider this third case, and then now let's consider the first and the second case that I just mentioned as really a simple extension, or essentially the same as the case where case of 2A ANOVA with no interaction. Okay, so let's look at this null hypothesis where alpha i's are all zeros. So in this case, we of course consider this guy xi dot dot, or in this case, so again, this is a male or female, and Korea, Japan, and the US, and then we have 10 different samples. And then we consider, we are concerned about this alpha i's being zeros or not. So we now consider the sample mean of all these guys, right? So this is called, x I dot dot, okay? And then also we obtain, we have the sample mean from this part. And then if alpha i's are all zeros, and then the sample mean between these two will be the same as the global mean, right? And so we are using the global mean here, right? Again here, what about the first way of computing the estimate of the sigma squared? The first way is actually the same as the one that we used here, okay? So the first, this guy, okay? So the first way of estimating the sigma squared is always true, regardless of any kind of null hypothesis being true or not, right? So we still use that in our denominator, okay? And then we now, for this new hypothesis or new null hypothesis, we only consider what will be our numerator, okay? And that numerator is computed in this manner. The sample mean, or the row-wise sample mean, okay, minus mu when the null hypothesis is true, because this guy, so their true mean will be mu, and then sigma squared, and then it is a sample mean, and then it is standardized by dividing it by square root of sigma squared divided by what? So how many samples do we have in each of these green and this pink bar? 10 times n, right? So n times L is the total number of samples corresponding to the first row and also for the second row. Yep, so that's why we see it in the numerator here. And then what is the degree of freedom here? Okay, so in this case, what is the degree of freedom of this guy? So let me ask a question to you guys. What is the degree of freedom? 뭐죠? So in this table, we used how many number of sample means do we consider? Just 2, right? So we just standardized each of them, and then the sum those squared of these 2. Okay, so the degree of freedom will be just 2 in this case. So degree of freedom will be m, right? But now we are using the approximate estimate of the global mean in the place of the true parameter of mu, right? And so this one is just simply one parameter to estimate, right? And so we have originally m degree of freedom, but if we replace them with our global mean, which is x, I think it's a typo. So I found one typo. So I should probably send the author of this book. It should be x dot dot dot, right? Because we are considering this kind of setting. Okay, so finally the degree of freedom will be m minus 1, right? Even though it's quite complicated, but if we consider alpha i's being 0, and then we just consider the row i's, right? Row i's. But the only difference is we originally had only one sample corresponding to these cells, right? But we now have, instead of an n sample, we have n times L sample. But because we are considering the row-wise effect, we just aggregate all of them corresponding to each row, right? Okay, then this guy, okay, divided by n minus 1 will be unbiased estimator because it's coming from the degree of freedom of this guy for the chi-square distribution. And then finally we obtain this test statistic, and this guy is used in the numerator, and then denominator was actually the same as this guy, right? Okay, so yeah, again, yeah. So if we are given in advance this significance level alpha value as maybe 0.05, and then we can reject or either reject or not reject the hypothesis. But we can also we can also compute this p-value as well, right? P-value. So in this case, this particular alpha value is not given in advance, right? Yeah, I think that's it. So yeah, in this case, yeah, let's just look at this example. I mean, yeah, it's a matter of just applying the equations that we saw in the previous slides in this particular example. So we have m different groups, or row wise, and n different groups, right? And then within each cell we have 4 different observations, and so L is 4, right? Yeah, and then the solution is just one single line where just applying the equations that we studied in the previous slide. And then these are the summary. Yep. So this error term, okay, which is used for estimating the sigma squared regardless of any hypothesis, right? And then when testing the row-wise effect, and there the numerator part will be used. I mean, in the numerator part, this guy will be used, right? Then, oh, there is another typo. It should be C, right? Okay, then for the interaction term, yeah, we already studied, yeah, this part to be placed in the numerator. Yep. I think that's it for the chapter 10. Any questions?
몇 페이지 전에요.
네.
NL 설명해주고 다시 설명해주시면.
네. 네, 요거요.
얘가.
Okay, so we are testing the hypothesis about alpha i's, right? So alpha I corresponds to different rows, right? So even though, although it is a little bit, it looks a little bit complicated, but when looking at the row wise, we have in this case 30 different samples in the first row, and then another 30 different observations in the second row, right? And then what we are doing exactly the same thing that we used in the just one way ANOVA. So we compute the sample mean of the first row, and that is represented as 1 dot in this case. Okay, so this is the sample mean of the first 30 observations, and then we apply mu, assuming that they have the same global or common mean value of mu, right? Okay, and then what is the variance of it? So this is a sample mean. So individual observation was sigma squared, but this guy is sample mean of n times L, or 30 different observations, right? So the variance will be reduced, and then this guy will be Gaussian distribution. Yeah, this is standard Gaussian distribution. Right? So that way, this guy is put or placed into the numerator. Any other questions? 네. 네, 이상적이네. 네. Okay, so yeah, some closing remarks in Korean. Yeah, so 네, 하여튼 하여튼 여기 있는 학생들 하여튼 그래도 열심히 수업을 들은 학생들 인 것 같아서 참 하여튼 개인적으로 굉장히 고맙게 생각하고요. 그리고 나 스스로는 이게 사실 내가 통계를 내가 학부 때도 그렇고 내가 배운 적이 없었는데 나는 하여튼 전기전자를 학부를 나오기도 했고 그거랑 상관이 있는지 모르겠지만 하여튼 그래서 여러 가지 연유로 해서 지난 1년 전에 또 요 과목을 1년 전에 요 과목을 처음 가르쳤고 요게 이제 두 번째로 이제 가르쳤는데 나 스스로도 한 두 번쯤 공부하니까 좀 이제 알 것 같아. 네. 그래서 좀 알 것 같다는 게 하여튼 뭐든지 공부할 때 이제 직관적으로 이렇게 좀 굉장히 깊숙이 좀 뭔가 좀 직관적으로 이해를 하는 게 하여튼 굉장히 좀 중요해요. 그러면 진짜 도대체 이해가 되지 않거나 이제 외워지지 않던 공식들이 이렇게 쫙 이렇게 들어오고 그런 것들을 쫙 이렇게 내가 쓸 수가 있게 돼요. 뭔가 그럼 좀 되게 뿌듯하고 좀 그런 게 있고 그런 게 생각보다 다양한 분야나 다양한 공부할 때 굉장히 생각보다 중요한 것 같아요. 그래서 하여튼 그냥 좀 깊이 좀 이렇게 직관적으로 좀 이렇게 좀 뭔가 체득을 한다 그럴까요? 그런 식으로 좀 공부를 좀 할 수 있기를 앞으로도 그렇게 좀 하는 습관이나 이렇게 좀 하기를 바라고요. 나 스스로 그래서 좀 그러니까 약간의 지난 1년 전보다 조금 더 스스로 만족스러운 거는 그런 직관이나 이런 게 나 스스로 좀 생겼던 것 같아요. 지난 학기에 비해서. 그래서 그런 게 조금이나마 더 좀 전달이 좀 여기 있는 학생들한테 좀 잘 됐으면 좋겠고요. 또 뭔가 좀 친해지거나 아니면 이렇게 좀 뭔가 개인적으로 이렇게 좀 이런 뭔가의 기회는 좀 많이 없어서 좀 아쉽긴 한데 그래도 그냥 여기 있는 학생들은 잘 따라와줘서 이렇게 가르치고 있으면 이제 얼마나 따라오고 있는지 이런 건 다 보이고 알잖아요. 뭔가 그래도 좀 내가 이렇게 좀 이렇게 전개하는 그 로직이나 이런 것들에 대해서 진짜 좀 잘 좀 따라온 것 같은 느낌이 좀 있어서 굉장히 스스로는 좀 굉장히 고맙게 생각하고 있어요. 네, 그래서 나중에 또 기회가 되면 또 이제 또 보겠죠. 그리고 혹시 여러 가지 궁금한 거나 장르에 대한 진로 상담이나 아니면 여러 가지 어떤 그거든 궁금한 거 있으면 편하게 연락을 하고요. 학기 그러면 잘 마무리하고 시험 준비도 또 잘 하고요. 예제 잔뜩 풀고 그러면 시험이야 이렇게 나오겠죠. 네, 그리고 또 방학도 또 알차게 또 잘 보내고요. 그리고 한 학기 또 수고 많았어요. 네. 시험 범위는 전범위. 예? 나중에 모르겠네요. 계산기 써도 돼요. 계산기 가져오고 와요. 70 한 장. 네. A4 한 장.
전범이라는 게 혹시 규명도 나왔나요?
좀 괴로워도 그렇게 좀 정리를 하는 게 좀 한 번 더 보면 이게 1년 가기 여기 10년, 20년이 가니까 좀
이게 분산 분석 부분 아니었고 회귀 분석하다가 갑자기 생각난 건데
네.
저희 시그마 제곱에 대한 불편 추정량으로 n-2분의 SSR을 썼잖아요.
네.
제곱값을 썼었는데 거기서
네.
그게
네.
시그마 제곱에 대한 불편 추정량이 될 수 있었던 근거가 시그마 제곱분의 SSR이
네.
카이 스퀘어 n-2 분포를 따른다고 한 거잖아요.
네,
그러니까
맞아요.
거기서 다른 부분에서도
네.
다른 부분은 어차피 그 카이 스퀘어 분포를 따른다는 걸
네,
직관적으로 딱 이해가 되는데
네.
보통 다 일반적으로 그냥 시그마 스퀘어에 대한 불편 추정량을 대입했을 때 자유도가 이만큼 감소한 카이 스퀘어 분포를 따른다는 게 약간 일반적인 이론 같은 거예요.
아, 그게 나도 그러니까 명확한, 그러니까 아주 그 구체적인 증명까지는 나도 잘 모르는데 일단은 그 yi가 따르는 이제 이게 분포가 이제 노멀이고 이제 이게 뭐냐면 예, 뭐더라 알파 i 플러스 베이타 i x i였나요? 이렇게 되잖아요. 이게 평균이고 이제 시그마 스퀘어도 이렇게 되는 거잖아요. 그러니까 yi 빼기 알파 i 마이너스 베이타 i x i 뭐 이렇게 해갖고 이거의 제곱 이게 그러니까 이게 결국은 이제 이 시그마 이게 에러였잖아요.
네.
이 에러는 그래서 평균이 0이고 분산은 이거를 따르는 게 되죠.
네.
네. 그래서 요거를 yi, xi 그 페어가 한 100개 있다. 그래서 이걸 다 썸을 하면 이거는 100 디그리 오브 프리덤이 100이 되어야 되는데 그쵸?
네.
근데 이제 우리가 이 yi에 대해서 그냥 평균을 여기다 만약에 그 여기에 실제 트루 민인 뮤가 들어가고
네.
이거를 이제 파라미터로 하면 이게 100 빼기 1이 되잖아요.
네.
그러니까 이게 비슷하게 이제 파라미터를 이제는 우리가 두 개를 쓸 수가 있는 거예요.
네.
이게 그러니까 얘를 우리가 좀 잘 맞추기 위해서 하나의 파라미터만이 아니라 두 개의 파라미터로 얘에 좀 더 가깝게 맞춰줄 수가 있는 거예요. 그러니까 이제 100 빼기 이제 파라미터를 두 개 썼으니까 이만큼의 자유도를 감소시킨다는 소리가 되거든요. 그러니까 그게 여기서도 지금 우리가 맨날 했던 파라미터를 몇 개를 우리가 쓸 수 있느냐 에스티메이터로서 에스티메이팅 해갖고 이제 좀 정확하진 않지만 어쨌건 데이터에 기반해갖고 이 값을 좀 더 이 y들에 좀 더 가깝게 만들어준다는 그런 측면 때문에 이 값을 좀 작게 만들어주는 거여서 그래서 이제 디그리 오브 프리덤이 이제 그 우리가 쓰게 되는 파라미터의 개수만큼 이렇게 빠지는 거예요. 그러니까 그만큼 줄어드는 거예요. 근데 리니어 리그레션에서는 y좌표과 기울기인 이 두 개를 쓰니까 이렇게 되는 거예요.
그것도 그런데 그게 카이 스퀘어를 간다는 게 직관적으로 와닿지가 않아요.
아, 카이스퀘어는 이제 여기서 갖는 거죠. 이게 좀 지저분해졌는데요. 아, 이거에서 베타 xi 이거가
네.
이거가 뭐냐면 yi가 이제 알파 i 플러스 알파 i 그냥 알파죠.
네.
알파 베타 xi 플러스 엡실론이잖아요.
네.
그러니까 얘네들은 다 디터미니스틱하다고 보고 얘가 이제 그거잖아요.
네.
가우시안이잖아요.
네.
그러니까 얘다가 얘만큼을 빼면 이건 그냥 엡실론이랑 똑같은 거예요.
그렇죠.
그러니까 이거의 제곱의 합은 그냥 엡실론 i의 제곱의 합과 똑같은 거예요.
네.
그러니까 이거는 가우시안이니까 가우시안 제곱, 물론 여기 시그마 제곱.
네.
이게 이제 카이스퀘어를 따르는 거죠.
그런데 요거는 카이 스퀘어를
네.
따르는데 여기서 그 저희가 알파랑 베타 대신에 알파 베타에 대한 추정량
그렇죠.
AB를 가지고 카이
네.
스퀘어 n-1을 따른다고
네.
하잖아요.
네.
그 과정에서 이 오차라는 녀석 자체는
네.
원래 확률 변수고 그거에 대한 추정량을 생각하는 것도 말이 안 되고 그거를 알파
네. 그게 무슨 말이에요?
그러니까 알파랑 베타를 대신해서
네.
이게 뭐라 설명드려야 되지? 그러니까 알파 플러스 베타 xi에 대한
네.
추정량으로 a 플러스 bxi를 저희가 쓰잖아요.
네.
근데 그 추정량으로 바꿔준 그 녀석으로
네.
그 카이 스퀘어를 쓸 수 있다는 것 자체가 약간 이해가 안 돼서.
그런 폼으로 쓰는 게
네.
그게 이제 더 이상 엡실론이 아닌데
네.
그렇게 따지면 그렇죠. 네. 네. 근데 그것도 뭐 다시 뒤쪽에서도 우리가
네.
하는 게 뭐 저렇게 뮤 뭐 x 닷 뭐 이런 거 집어넣으면
네.
다시 그거가 이제 정확하게 그게
거기서는 직관적으로 딱 그 노멀 디스플레이션 변수를 따르니까
네.
그거에 대한 평균과
네.
분산이 딱 와닿는데 여기서는 그게 딱 와닿지가 않아서.
이게 그러니까 어떻게 보면 그냥 yi에다가 어떤 평균 그러니까 어떤 고정된 뮤를 에스티메이트를 해주는 어떤 뭐 y 바 같은 걸 쓴다.
네.
이러면 이건 카이스퀘어를 따를 거예요, 그죠?
네.
근데 이 y 바를 이 y에 따라서 y가 가지는 얘가 yi가 가지던 xi 있잖아요. 이거의 함수로서 이 y 바를 조금씩 더 바꿔주도록 얘 좀 더 가까운 평균을 이렇게 해주도록 한다. 약간 이런 개념으로 좀 봐야 될 것 같은데. 근데 지금 이야기한 것처럼 이게 고정된 값, 그러니까 이거를 정확한 값을 이렇게 역시 고정된 하나의 상수 값을 정확한 값이 아닌 에스티메이터로서 썼을 때는 그게 뭔가 이해가 가는데 그게 뭔가 변동이 되는 값이라서 좀 거시기가 되는 거죠.
네.
좀 이해가 되는데 뭐 그냥 뭐 정확하게 나도 설명을 못했어요. 근데 그 애초에 그게 크게 다르지 않다. 뭐 그런 어떤 측면에서 이게 여전히 카이스코를 따르고 뭐 이렇게 되거든요. 나도 정확한 그걸 답을 주기가 어렵겠네요.
일단은 받아들이는 걸로.
네. 네.
저는 사실 제가 그걸 느끼기 시작해서 그렇긴 한데
네.
그 xi 다시
네.
네, 그러니까 이거랑 비슷한 폼으로 나오는데 왜 그 m의 자유를 가진지 잘 헷갈리거든요. 왜냐면 이거 자체도 어쨌든
네.
xi 행에 있는 것들을 하는 거죠. 그 xijk 하나하나도 다 확률 분수잖아요.
네.
근데 걔네들도 정규 분포를 따른다고 가정하는 거 아니에요?
네.
그러면
네.
xi 도 걔네들을 합친 거니까
네.
카이스케어를 따르는 거 아니에요? 그러니까 자유도가 제 생각에는
네.
m뿐만 아니라 행 개수 m만 아니라 그 j
네. 그러니까 이게 지금 이 세팅은 지금 그러니까 로우의 이펙트를 볼 때는요.
네.
컬럼은 지금 뭔가 이펙트는 그냥 없이
네.
네, 그래요. 그러니까 이거는 네. 컬럼에 대해서의 이펙트는 그냥 없다라고 가정을 하고 지금 들어가는 것 같아요.
네.
그래서 이게 지금 얘가 물론 이 나라에 대한 이게 코리아, 재팬, 유나이티드 스테이츠면 나라에 대한 이펙트는 뭔가 있을 수도 있고 그게 그러면 이 평균이 다 다를 수가 있는데 이 내에서 네. 그걸 물어본 거라면 그거는 그 이펙트는 없다라고 지금 가정을 한 것 같아요.
그러니까 약간 이것만 주목하는 거니까 얘네들은
네.
변수로 가정 안 하고 그냥
그런 것 같아요.
통째 본다는
네.
거.
그런 것 같네요. 네. 중요한 지적이네요. 네.
그리고 제가 좀 몰랐던 게 있는데
네.
p-밸류를 구하는 거는
네.
그 어떠한
네.
그 상황에 따라 달라지는 건가요? p-밸류는
네.
따로 구하는 방법이 일반화된 게 아니라 그냥 분포에 따라서 다르다는 건가요?
우리가 그러니까 이게 이제 F 디스트리뷰션을 따른다라고 할 때,
네.
이 F 디스트리뷰션 따른다라고 할 때, 이 값이 예를 들면 3.8이 나왔어요.
네.
네, 요 값이. 근데 이게 지금 요 디스트리뷰션을 따르는 거예요. 요 알파는 지금 없다라고 생각하고요. 그러면 요 3.8이 카이스코어 디스트리뷰션이 대충 이렇게 그려질 텐데 3.8이 한 이쯤 발견이 된 거잖아요.
네.
그러면 이 3.8은 이게 한 대충 평균 이 값 1 근처로 해서 발견이 될 텐데 3.8이라는 값은 꽤 이렇게 좀 극단에 치우친 값이잖아요.
네.
그랬을 때 이 값 그리고 이거보다 더 극단적인 값은 3.81, 3.82, 3.9, 4.0 뭐 이런 값들을 다 포함을 하겠죠.
네.
그래서 우리가 관찰한 요 테스트 스태티스틱에서 나온 요 값과 그 값보다 더 극단적인 값들을 이제 가지게 될 그 확률값 이걸 이제 p 밸류라고 하거든요.
이 확률 값이요?
네, 요 값을 p 밸류라고 해요. 그래서 요 밸류가 만약에 3.8 이게 뭐 한 7%다.
네.
그러면 이거는 5%의 유의 수준으로 검열하겠다 그러면 5%는 여기서 이렇게 잘리거든요.
네.
이쪽으로 가야 되니까 이거는 널 가정을 리젝트 하면 안 되겠죠.
그러니까 기각을 해도 그게
기각을 하면 안 되겠죠. 5%라는 얘기는
네.
이쪽에 이제 5%에 해당하는 요 값이
네.
있을 때 이 값이 여기가 5%일 때는 여기가 뭐 한 4.3이었어요.
네.
그러니까 4.3보다 더 큰 값이 우리의 테스트 스태티스틱으로 나와야 우리는 널 가정을 기각을 하는데 우리는 그거보다 이제 못한 값을 만들어냈고 그 왜 못한 값이냐? 거기서부터 더 극단적인 값들의 어떤 확률의 총합은 7%다. 즉 5%보다 더 큰 거예요.
네.
네. 그래서 이제 이거는 가정을 기각을 하면 안 되는 거죠.
네. 그러니까 그 기각을 한 그러니까 그게 거짓인 상태에서도 이 결과가 나올 수 있기 때문에 그런가.
아, 그러니까 널 가정을 만족했을 때,
네.
널 가정을 만족했을 때 3.8이라고 하는 값은 어느 정도 관찰이 충분히 가능한 값이라고 보는 거죠. 95%의 어떤 그걸로 따지면 3.8은 뭐 우리가 충분히 관찰할 수 있는 값이다. 그러니까 이 우리가 이렇게 가정한 참이라고 가정한 널 하이포테시스가 거짓이라고 얘기하면 안 된다.
그러니까 p-밸류가 그 가설에 따라서 나오는 그런
네.
값이고.
네. 다 이제 p-밸류나 이제 알파에 의한 그 어떤 그 가설 검정은 다 널 하이포테시스가 이제 true라고 가정할 때를 일단 시작으로 해서 요 테스트 스태티스틱이 이 널 하이포테시스가 이렇게 참일 때 얼마나 이게 그러니까 관찰하기 힘든 값이냐 요거를 판단하는 거거든요. 그래서 일반적으로 p-밸류가 뭐 이런 어떤 우리가 관찰한 값이 뭐 5.8이 나왔다. 그리고 이때 p-밸류는 0.0001이다. 뭐 이거는 네 95%뿐만 아니라 99%, 99.9%로 이렇게 해도 얘는 기각이 되는 거죠. 그러니까 정말 보기 힘든 케이스다 이거죠.
그럼 그 마지막으로요.
네.
그 우도라는 거를
네,
애매하게 설명해서
네.
그래서 우도라는 게 뭘 말하는 건지 좀 잘 모르겠어요.
라이클리후드는 그러니까 뭐 이런 거예요. 그러니까 지금 데이터가 아니면 우리가 따르는 디스트리뷰션이 여기인데 3.8을 관찰할 어떤 확률 밀도로 따지면 이 값이 되는 거예요. 이 3.8.
확률 밀도의 함수값이 우도.
네.
근데
우도가 이제 보통은 데이터를 여러 개를 따지잖아요. 뭐 한 5개 데이터 아이템이 발견이 됐어요. 그러니까 뭐 3.8, 2.3 뭐 이게 뭐 사람의 키다 그러면 뭐 우리는 이제 173, 180, 뭐 165 뭐 이런 값을 발견을 했어요. 그러면 얘네들이 따르는 우리가 잘 모르지만 얘네들이 따르는 확률 분포가 만약에 이렇게 생겼어요. 그러면 얘를 관찰할 확률 밀도는 이만큼에 해당이 되죠. 그러면 이때는 이 디스트리뷰션에서 얘네들을 관찰할 확률은 뭐 생각보다 높지 않은 거예요. 근데 이제 우리의 디스트리뷰션을 만약에 이렇다라고 가정을 한다면 이때는 바가 훨씬 더 높잖아요. 그러니까 그러니까 이 바들의 어떤 곱을 우리가 따지거든요. 이게 주사위를 이렇게 던질 때도 그 확률 3이고 뭐 3보다 크고 뭐 짝수인 뭐 그거는 2개 곱하잖아요, 확률을. 이것도 데이터가 우리가 178도 관찰했고 180도 관찰했고 165도 관찰했고 뭐 이걸 하나하나를 이제 동시 사건으로 곱을 해줘요. 그래서 이 4개의 어떤 그 바의 높이를 다 곱한 그게 어떤 이 확률 분포를 기준으로 했을 때 우리가 지금 현재 갖고 있는 요 픽스드된 고정된 요 데이터를 생성해낼 수 있는 어떤 그 확률이 되는 거죠. 이 확률을 제일 높여주도록 하는 이 디스트리뷰션은 어떻게 생겨야 되느냐? 그러니까 이거보다는 이게 더 나아 보이고요. 그다음엔 이렇게 되는 거 말고도 또 뭐 예를 들면 또 뭐 이렇게 쪼렷하게 생긴 이거는 여기서는 굉장히 높죠. 근데 여기서는 굉장히 작죠. 그럼 이 4개의 값을 곱한 게 좋을 것이냐? 이렇게 쪼렷한 디스트리뷰션에서 요 값 4개를 곱한 게 더 이렇게 좋을 것이냐? 이걸 우리가 판단을 해서 그 파라미터를 결정해 주는 거죠. 그게 이제 MLE.
ML이요.
그러니까 맥시멈 라이클리후드 에스티메이션.
그럼 그 추정량은 그 저희가 관측한 뭐 표본 값이나 그걸 통해서 그냥 뭔가 공식을 통해서 나타낸 값인 건가요?
추정량? 추정량이 영어로 에스티메이터. 그렇죠. 에스티메이터는 추정량 그러니까 우리가 잘 몰라요. 그 진짜 값을. 근데 걔를 이제 추측하기 위해서 우리의 데이터에 기반해서 걔가 얼마일 것이다라는 어떤 그런 말 그대로 추정을 한 그 값이 되는 거죠.
그러니까 구하는 거는 공식으로 딱 나오지만 그거는 참값에 비해서 뭔가 어떤 분포를 가지고.
그렇죠. 참값이랑 좀 다를 수 있죠.
감사합니다.
네.
마지막으로.
그래요.
그 공식 중에 SS가 그 최소 제곱 그거잖아요. 근데 SSR이 또 나오는데 이거는 왜 굳이 2번 얘기한 거예요? 식이 똑같이 생겼는데.
이게 sum of squares of residual일 거예요. sum of squares of residual.
근데 여기서는 이건 입실론의 제곱의 합이잖아요. 근데 입실론과 그 레지듀얼이 다른가요?
그게 어디 나왔던 거죠? 리그레션 쪽에서 나왔던 건가요?
아까
그래요?
얘기했던 쪽에서. 이거 전에 나왔을 거.
그래요? 이게 전에? 그냥 SS가 있었어요.
네.
그래요? 가르쳐도 난 모르네요. 뭐야? SS? 혹시 어디서 나왔는지 아나요? 아 이거 예, 그래요.
그러니까 이거는 그 레지듀얼이랑 개념이 다른 건가요?
네, 이거는 그러니까 어디서 보자. 레지듀얼이랑 이거 똑같은 건데요?
아 그냥
네,
한 번 더 언급만 해주는 거예요?
네,
아,
네. 예, 똑같은 거예요. 그러니까 여기서는 이게 그러니까 내용 자체가요.
네.
이거에서 이게 등장한 어떤 이 책에서의 이 맥락이나 이 내용은 이제 이런 어떤 차이를 우리가 이렇게 좀 목적 함수라고 부르는데 요거를 최소화를 시켜주도록 하는 A, B를 한번 찾아보자. 가 되는 거고요. 그 다음에 그런 A, B를 찾았어요. 그래서 요거를 대입을 했어요. A, B에다 그 특정한 값들을.
네.
그래서 실제 결과적으로 나오는 이 값. 그러니까 이 값이 A, B에 따라서의 이거는 지금 현재 함수인 거예요. 이거는 F의 A와 B에 따라서 이게
네.
막 달라질 수 있는 함수인 거고 A와 B가 결정이 되고 나서의 이 결과적으로 나오는 요 값이 얼마냐. 그게 이제 SSR이 돼요. 근데 같은 의미라고 보면 될 것 같아요. 식자체.
감사합니다.
네. 네.
그 감마 할때
네.
그 이렇게 시간 아까 설명해 준 제가 잘못 들은 건가 싶어가지고
네.
했는데
네. 전체
전체 다 더하면은 0이 아니라고 하셨나요?
전체 다도해도 0이죠.
네.
근데 전체 다도해도 0일 뿐만 아니라 각
각각에
컬럼별로 그렇죠. 각
그러니까-
컬럼별로나 로우별로 더해도
제가
0.
잘못 알아들은 게
네.
그러니까 전체 다 더하면 0이 아닌데 각각에 더하면 0
아,
이렇게
네네네네.
알아들어가지고
네. 이 전체를 더해.
네.
이거 좀 잘못 내가 뭐 좀 다 더해도 0이 될 거고요, 당연히.
네.
그러니까 이게 각각이 0이면 더해도 0일
더해도
거죠. 그렇죠.
그리고 아까 그
네.
메일 피메일하고 코리안 재팬
네.
이야기에서
네.
그 칸 안에가 10이라고 하신 게
네.
그 이제 그 L이 10이라고 하신 건데
네.
그럼 그 L의 기준은 수업하시면서 말씀 안 해주신
L
L의 기준 그러니까 예를 들면
기준. 네.
뭐 그 M은 지금 성별이라는 기준이 있고 N은
의미가
이제 그
네.
나라라는 기준이 있는데
그렇죠. 네.
L은
기준이
그냥
없어요.
말씀 안 하신 거예요.
네, 기준은 없고
네.
저거는 그냥 그 저거를 만족하는 그러니까 남자와 코리아를 만족하는 그 어떤 속성을 가지는
네.
옵저베이션을 그냥 10개를 뽑은 그러니까 반복 이렇게 샘플링을 하는 그 반복 횟수.
그러니까 그 아까 이그젠플에도 보면은
네.
이제 그 이그젠플이 맨 마지막쯤에
맞아요. 한 4개짜리 있었던 거.
네.
네.
그게 이제
네.
온도 있고 메테리얼
네.
있고 이 안에 4개가 이제 L4라는 얘기인데
네.
그게 L4라는 얘기가 그냥 이거 4번 했다 이런 얘기.
맞아요. 네. 내보냈다. 그거예요.
그러면은 이걸 조금 응용하면
네.
뭐 사실 의미가 없을 수도 있는데 그 2개짜리 그러니까 하나짜리로 만들고 그 안에 거를 이제 그러니까 예를 들면
네.
MN 그러니까 L 생각 안 하고 이제 MN 2개만 있었다고 할 때
네.
그러면 이제 이거를 N업 이제 이렇게 안 쓰고 그냥 이렇게 쓰면 그렇게 표를 줘도 알아서 이제 N을
그렇죠.
구해야 돼.
그렇죠. 그렇죠. 네. 그렇게 봐도 되죠. 네. 그게 여기 unequal size 뭐 사실 이거의 개념인 셈이죠. 그렇죠. 그러니까 unequal size였고 어디 갔어?
근데 어니콜 사이즈랑
네.
좀 다르지 않나요?
네.
어니콜은
네.
각각이 다 다를 수 있는데 L이 만약에 정해지면 다
정해졌다.
그러니까.
네. 그렇죠. 맞아요. 네. 이렇게 그냥 뭉뚱그려서 그냥 쭉 옆으로 나열하는 게 아니라 그냥 순서 없는 뭔가 그렇게 보면 되는 거죠. 원웨이에서. 네.
제 학부 마지막 강의였어요.
그래요? 네. 그